Good morning, everyone. Um, any questions about last time's lecture? Good morning, Professor. To be in echelon form, does the number in the top left corner have to be a leading entry? Okay, I will read your question again, Haley, and try to understand it. In order for a matrix to be in echelon form, does the number in the top left corner have to be a lead? Not necessarily. Good question. Not necessarily. Sometimes in extreme cases, we can have that. So the only way it cannot be a leading if we have 0 in the first column. But after that, you should have something like this and then bunch of 0. So not necessarily, but if you don't have leading here, it means everything below it has to be a 0. Okay, make sense? All right. Any other questions from the homework? Wouldn't you have a next subset in the system at all? You will have. You will encounter cases when it will end up being 0, 0, 0. And what's happening in this situation, which is something we will start today, is that the variable that correspond to this column can take any value we want. That's the situation that will happen. So we will call it a free variable. It means it can take any value we want, something that you will start to work on today. Good questions. Any other questions? How about the homework? Did you guys do the echelon form? Are you comfortable with it? It's crucial. As I said, that's the only technique we will learn in this class, so you have to know it extremely well. All right. Okay, so we move on today. Before I start, I will talk a little bit for 2 minutes about the geometry of the solution. So let us recall from last time, from the first lecture, I guess. Okay. When I asked you, I gave you, let us say, an equation, a linear equation in 2 variables. And I asked you, how can you interpret the solution geometrically? And you guys say, okay, every solution is going to be on the point on the line, which is given by this equation. Now, we are used all the time to call this is x and this y. Now, in this class, sometimes we use x and y, and sometimes instead of the x, we call this the x1, and this is the x2 axis. So with this in mind, every solution is a point on the following line. I draw the line, x2, 0, x1 is 1, x1, 0, x2 is a half. So every solution is a point on this line. Every solution is a point on this line. Now, let us say we have the following equation. Let us say I have the equation 3 unknown, x1 plus 2x2 plus x3 equal to 2. Let us say I have this equation. So that's equation with 3 unknown, x1, x2, and x3. How can you visualize the solution of this equation? Now, I know that some of you had calculus 3, some of you didn't have it, but it's not really hard. This is equation of a line in the plane. This is anybody equation. That's equation of what? Anybody knows? Exactly. That's the equation of a plane in what we are going to call very soon R3. It means in 3 dimensions. Okay, so every solution of this equation is actually going to be a point on the plane. So in a plane, we will call this is x1, which is the x-axis. The y-axis, we call it x2. And the z-axis, we call it x3. Okay, and every solution is a point on the following plane. So let's see how can we sketch the plane. I need 3 points to sketch a plane. So I can take x2, 0, x3, 0, x1, 2. So that's a point here, which is 2, 0, 0. Now if I take x1, x3, 0, x2 is 1. So this is a point here, 0, sorry, a point here, 0, 1, 0. And finally, x1, x2, this will give me 0, 0, 2. So every solution is actually a point on this plane right there. Okay, and this will help us a little bit understanding the solution we are going to get for some system very soon. So in R2, it means if I have two unknown, the solution is all point on this line. If you have three unknown, the solution is point on the plane. Remember, said the same way the line is infinite, the plane is also infinite. So this plane right here. Okay, so this is a note about the geometry of the solution to unknown and three unknown. Okay, today we are going to start learning how to solve a system. So we're spending the whole hour basically learning solution of a system. So I start with my first system. The question is how to solve a system. Okay, step number one, of course, you have the system. So the way we are going to solve a system, we take the system, we associate to it, we take the augmented matrix, we associate to it the augmented matrix, we row reduce to augmented matrix, row reduce to echelon form, and we stop right there. And I tell you what we do after this. Okay, so first we take the augmented and we row reduce to the echelon form. So that's exactly what we are going to be doing today. So the augmented matrix, it's a 1, 1, minus 1, 2, and a 1, a 1, a minus 3, 0, a 0, a 1, a minus 1, a 0. Okay, so we want to reduce it to echelon form. So as we did last time, since I don't have the scenario 0, 0, 0, so I will start in here. That's my leading. I'll use, as I'm doing the row operation, you also do it in your head, just to make sure you totally have a control over those operations. So I will use this leading to make this into a 0. So the natural row operation is, I'm going to take the first row, multiply it by 1, add it to the second, and this is going to be my new R2. Okay, and this will lead me to the following. 1, 1, minus 1, a 2, 0, minus 1 plus 1 is a 0, minus minus is a 1 minus 3, it's a minus 2, minus 2. As I'm doing those, please make sure I do the computation correct. 0, 1, minus 1, 0. So that's the first operation. And now I have a bunch of zeros, so I'm basically eliminating this x1. Now I move to the right, down. I need to create a leading right at this position. Now, the only way to create a leading, I have to interchange those two rows. So the second operation we're going to do is we're going to R2 and R3. And this would lead me to the following. 1, 1, minus 1, and a 2. 0, 1, minus 1, 0, 0, 0, 2, 0, 0, minus 2, minus 2. So 1, I have here a leading. I'm fine. Below it is a 0 to the right and to the left. But this is also a leading. So I'm basically in echelon form. Now to make my life a little bit easier, I'm going to divide by minus 2. You don't have to, but it's just make things a bit easier. So I'm going to scale the last row. 2, 0, 1, minus 1, 0, 0, 0, 0, 1. You don't have to, as I said, but I think this makes it think easier. Right? Now I am in echelon form. I stop right there. So in echelon form, I'm going to stop. And then we write the system that corresponds to this augmented matrix. So once you hit the echelon form, you write the system that corresponds to this augmented matrix. So let us write the system. So row reduce to echelon form, then write the system. So now the system is x1 plus x2 minus x3 equal to 2. x2 minus x3 equal to 0. And the last one is x3 equal to 0. The main idea behind those row operation is, the crucial idea is that every value that solves this system solve that system. It means the simple system here and the original system are equivalent. They have the same solution. Row operation do not alter the solution of the system. Now, can I solve the system very easily? Quickly. Can I solve this system very easily? Yes, what did we call that? What did we call it? Back, yeah, we gave it this name. Now we're gonna solve by we use the word back substitution. Somebody is, okay, all right. Now we are going to use back substitution to solve the system. Okay. X3 is 0, so we're done with X3. X2 is equal. Sorry, my apology. You guys should tell me if I do something wrong. X3 is equal to 1. My apology. X3 is 1. X2 minus X3 is 0, and this. So this will give me X3 is 1. Now I back up. X2 is X3. So X2 is equal to 1. And then I back up. X1 is 2 minus X2 plus X3. It means X1 is 2 minus 1 plus 1, which is equal to 2. So this is the back substitution. And the solution is, so far we are writing the solution as a list of 3 numbers. So it's a 2 for x1, and it's a 1 for x2, and a 1 for x1. So that will be the solution. Thanks, Dylan. That will be the solution of my system. Now I can take those, plug it back into the initial, and this has to be satisfied. 2 plus 1, 3, minus 1, 2, check. 2 plus 1, 3, minus 3, 0, check. 1 minus 1 equals 0, check. And this is the solution of the system. So that's really be the process in which we are solving this whole system. Any questions? Okay. Now, based on the geometry that I've mentioned in the beginning of the lecture, what does the solution 2, 1, 1 represent geometrically? A point in space, exactly. Which point in space? Let's be very, very clear. Which point? The point where the 3 planes intersect. Exactly. So that's the same idea. Every solution 2, 1, 1 satisfies this equation. It means this point is a point on this plane. It's a point on this plane. It's a point on this plane. It means that those 3 planes, if you draw them, they're going to intersect, and they intersect in exactly 1 point, which is 2, 1, 1. Okay. Any questions before I move on to example number 2? So we're going to do a lot of examples. Of course, each one of them is different than the one before. All right. Example number 2. Solve the following system. x1 plus x2 minus x3 equal to 2x1 plus x2 plus 2x3 equal to 4. 4x1 plus x2 plus 8x3 equal to 0. And the solution is always the same. We take the augmented matrix and we reduce it to echelon form. Because when we hit the echelon form, we can do back substitution. That's the goal of the echelon form. All right. So let's get going. As I said, watch my arithmetic. I can do mistakes in this stage. It's a 1, 1, minus 1, 2. I try to make all my system easy. I don't want the echelon of the computation to get into the way. It's a 2, it's a 1, it's a 2, and a 4. A 4, a 1, 8, 0. So echelon form. First, I need to create a leading right there. I already have a leading, and I'm going to use it to make a 0 in here and a 0 in here. Okay. So to the first line, sorry, the first row, I'm not touching. Now I want to make a 0 in here. So I will take the second row, the first row, times it with 1, add it to the second, and that would be the new second row. Okay, so I'm going to hide this a little bit. Minus 2 plus 2, it's a 0. Minus 2 plus 1, it's a minus 1. Minus 2 times that's 2 plus 2, it's a 4. Minus 2, which is minus 4, plus 4, which is a 0. Okay? Now, to make our life easier, we can do 2 row operation at the same time, very carefully. So instead of writing 4, 1, 8, 0, and then again go back, multiply this by minus 4 and add it, I can do those at the same time. So I'm keeping this one fixed. I'm multiplying this by minus 2 to make this 0. And at the same time, just to make things a bit faster, I'm going to do 2 operations at once. So I'm going to take the first row, multiplied by minus 4, add it to the third, and this would be my new third. So I'm not touching this row. I already took care of it. I used the first row to make this into a 4. So this would give me a 0 in here. Minus 4 plus 1, it's a minus 3. Minus minus 4 plus 8, it's a 12. Minus 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 8. Okay? All right, now I keep going. This is a 1. I'm fine here. Everything's 0. Write down. I have a leading here. I need to use it to make what's below it to be a 0. All right, and let's do that. And remember, I stop when I hit the echelon form of the matrix. So the first row hasn't been. The second row. Now the third row. I need to multiply the second row by a minus 3, add it to the third, and this would be the new row 3. So minus 3 times 3, that 3 minus 3 cancel each other out. Minus 12 plus 12, it's a 0. Minus 3 times 0, it is 0. Minus 8. Okay, so this is a 1. That's my leading. I move to the right, go down. There's a 0. I cannot do anything. And this is basically my leading. Am I in echelon form? Yes or not? Am I in echelon form? Absolutely. So we are in echelon form. So when you hit the echelon form, you write the system that corresponds to it. So let's write the system that corresponds to it. And you guys should be thinking at the same time I'm writing. So what's the system that corresponds to it? Okay, the first equation, read x1 plus x2 minus x3 equal to 2. The second, read minus x2 plus 4x3 equal to 0. How does the last equation, the last row, how do you read it quickly? How 0 x1 plus 0 x2 plus 0x3 equal minus 8. 0 equal minus 8. What does this mean? What does this mean? Can this last row be possible? Is it possible to have 0? Absolutely not. It means the system. So this one cannot occur. What does this mean? It means if we try to solve the system, I'm having nonsense at the end. It means the system is inconsistent. And we know that this can occur. We know that this occurs, so this tells me that we have an inconsistent system. It means, as you guys wrote, there is no solution to the system. It means no values x1, x2, x3 can solve the system. Okay? Geometrically, please, if I go fast or anything, you have to let me know. Geometrically, what does it mean? What does it mean geometrically? So here I have 3 planes, basically, and the solution is, there is no solution. What does this mean? What can you say about those 3 planes? And intuitively, it means the planes do not intersect. They don't have to be parallel. They don't have to be parallel to each other. They just do not intersect. Now, the book has a picture. I will try to put it in front of you. It's better than anything I can draw, I guess. Okay, so this is really the picture. That's really the picture. This is a plane, and this is a plane. Those 2 planes intersect along this line. And that's the 3rd plane. It does not touch this line. It actually intersect the greenish one, it intersect the bluish one, but it does not intersect them along this line. So this is exactly the picture that this system represents. 3 planes, they do not intersect. There is no solution. Okay. So this would lead us to the first rule in terms of solving a system. So whenever we have a system, when the system doesn't have a solution, the system does not have a solution. Whenever you do the echelon form, and the echelon form has a row of this form, the last term is not 0, the rightmost term is not 0, it means the augmented term is not 0, and everything before it is 0. That's immediately the system have no solution. So I usually write it as a rule number 1 because we have to start learning those. So rule number 1 is exactly what I did a minute ago. So rule 1. If the echelon form of the augmented matrix of a system has a row of the following form. Everything 0, the rightmost term, the book call it B, I'm using the same B, where B is non-zero, then the system is inconsistent. So the minute you hit a system and you have a row of this form, immediately the system is inconsistent. And the reason behind it, which is what you guys said, and this is because the row 0, 0, the augmented term is non-zero. Read 0x1 plus 0x2 plus 0xn equal b with b different from 0. It means it reads 0 equal b with b different from 0, then there is no solution. Okay, so whenever we have a system, we encounter this scenario, immediately we can deduce we have inconsistency. Questions, please. Okay, as last time, if I'm moving the paper before you guys are done, you let me know. Very good. All right, more examples. As I said today, we will do a lot of examples. Each one should be a variation of a different one. So example number 3. So the following system. x1 plus x2 minus x3 equal 2, 2x1 plus x2 plus 2x3 equal to 4, and 4x1 plus x2 plus x3 equal to 8. Okay, we always solving the same pattern. We take the augmented, We're going to reduce it. We stop at the echelon form and see what is going on. All right, let's get going. I have to use a pencil because I do mistakes. So this is my system, 1, 1, minus 1, 2. And a 2, a 1, a 2, and a 4, and a 4, a 1, 8, and 8. As I said, if I do any mistake, please let me know. So this is my leading. Right here, I'm going to create a 0 here and a 0 here. And I will do exactly sorry, what I did last time. I'm going to do 2 operations at once. So 1, 1, but very carefully, very carefully. I'm going to multiply the first row by 2, add it to the second, and I will make this into my new row 2. So minus 2 plus 2, 0. Minus 2 plus 1, minus 1. Minus 2, that's a 4. Yeah. And then minus 4 plus 4, it's a 0. Now this row, it's 4 R1 plus, I meant minus 4 R1 plus R3. And this will become my new R3. So minus 4 plus 4, it's a 0. Minus 4 plus 1, which is a minus 3. It's a 12. And minus 4 minus 8 plus 8, it is a 0. Okay. Now I'm going to proceed. So I have a 1 in here, a minus 1, and a minus 3. So I'm not in echelon form. I have to create a 0 in this position. So my operation is I take this row, the second row, multiplied by minus 3, the second row. I add it to the third, and this would be the new row 3. Okay, so I did not touch the first row. I do not touch it anymore. It did its job. I don't need to touch this one. And now here, 0. Multiply this by minus 3. Minus 3, that is plus 3. Minus 3, it's a 0. Minus 12 plus 12, it's a 0. And this is a 0. Okay. All right, so this is my leading. Always emphasize those. To the right, I am in echelon form. All right, so I can stop here, but since it's a minus 1, I will scale it just to make this one. You don't have to at this stage, but it will make things a bit easier. So I multiply this, so I'm just scaling now for the ease of the operation. So it's a 1, 1 minus 1 is 2, 0. So I multiply across by minus 4. Any mistake will mess you up. That's 0, 0, 0, 0. Okay. I am in echelon form. So this one is in echelon form. I do not write the system till I hit echelon form. So that's what I have to hit it. 100% echelon form I hit. And once I hit the echelon form, then I write the system that corresponds to this echelon form. That's what we did before. So x1 plus x2 minus x3 equal to 2. x2 minus x4, sorry, minus 4, x3 equal to 0. And this is, do we have inconsistency in this scenario? Do we have? No, because this reads 0 equals 0. So that is nothing big deal. 0 equal to 0. So I'm stuck here. How I'm going to solve the system, right? First, let us remember everything that solved this original system solved this system. This system and this system have the exact same solution. It means every 3 numbers that satisfy those 2 equations will satisfy those 2 and vice versa. So now what's really happening? How are we going to solve the system? And let me ask you the following questions. Let us say I give you x3 equal 1, okay? Can you solve for x2 so that this equation is satisfied? If I give x3 equal to 1, and I use back substitution, I can solve for x2. I will get x2 equal, so we have x2 minus 4x3 equal to 0. This is going to give me x2 equal 4x3 equal to 1. If I know x2 and I know x3, do I know x1? I can use this equation to find x1. So this will give me x1 equal 2 minus x2 plus x3. It means x1 equal 2 minus 1 plus 1 equal to 2. So if I give x3 to be 1, x2, 1 will solve this equation. Isn't x2 minus 4? So this has to be 4. Thank you. That's why I told you to guys watch me carefully in this. Okay, so this is gonna give me 2 minus 4 plus 1, which is equal minus 1. So this tells me that minus 1, 4, 1 solve those equations. So if I put here 4 minus 4, I get a 0. Minus 1 plus 4 will give me a 3. 3 minus 1, 2. Those numbers satisfy those two equations. It means they will satisfy the other equation. Now, I can also give, I don't have to give x3. Suppose I said, okay, I want x3 to be equal to 0. I can do the same thing. I can do the back substitution. Then I can take x2 to be 0. And then x1 will be 2 minus the equal to 2. It means again 2, 0, 0 is a solution. So what I'm trying to say? What am I trying to say? Suppose I give x4, x3 the value 100. Can you find x2? Yes or no? So that this x, if I know x2 and I know x3, can I find x1? If I have a value for x3, which is 100, x2 will be 400, I can find x1. Is it all real numbers? Yes. So what does this mean? That every time I give x3 a specific value, I can generate a new solution. So this is a situation where I am going to have infinitely many solutions. Every time I assign to x3 a different value, and as you realize, I can if I give x3 any value I want, real number, because we're working with real numbers. So I can actually give x3 the value square root of 2. There is nothing which stop me from that. If I give square root of 2, then x2 is going to be 4 square root of 2. x1 is going to be 2 minus 4 square root of 2 minus square root of 2. So I can give really x2 any possible value, x3. Every time I give x3 a different value, I generate another solution. So this is definitely the situation where I have infinitely many solutions. Infinitely many. Okay. Now, what we are going to call x3, we're going to give it a name. Since x3 can take any possible value, we will call x3 a free variable. And you don't have to write. We're going to define this rigorously in a second. So x3, we will give it a name and we will call it a free variable because it actually can take every value it wants. x1 and x2 will be called basic variables or sometimes constrained variable. Constrained because they are constrained by the value of x3. So some books use the word constrained because they are constrained by x3. They cannot take any value they want. This book is calling them basic variables. So they are calling x1, x2 basic variable. So before I start defining those two ideas, geometrically, is it possible for three planes to have infinitely many solutions? before we start the vocab? I read your question, Samudra, but first let me talk to geometry and then I tell you, answer your question. Okay, geometrically, does it mean for three planes to have infinitely many solutions? How can the picture show up? All three planes intersect in a line, absolutely correct. That's the situation where you have a plane, plane one, plane two. I'm not very good in drawing in three dimensions, especially on paper like this. So the second plane can go like this. So those two planes are intersecting along a line. The third plane, again, it will intersect along the same line. So the third plane can be something like that. Intersect along the same line. So that's the situation where you have three planes intersecting along the same line. So that's why it's very possible to have infinitely many solutions. Okay. Now, how do we choose the basic? How do we choose a variable? And this will answer your classmate question. The way the choice is going to be is the following. And that's the easiest choice. X2 will give us problem. We're going to go to the echelon form and the matrix. So this column will be called the column that corresponds to X1. This would be called the column that corresponds to X2. And this would be the column that corresponds to the variable X3. And this is the augmented column, the column that gives me the constant term in the system. When we're solving and we know that the system is consistent, like in this situation, the column that does not contain a leading, the column that doesn't contain the leading, the variable that corresponds to it will be the free variable. So the free variable will be only the variable that corresponds to the column without leading. The variable that corresponds to the column with leading will be what we will call the basic variables. And that's exactly what I'm going to define right now. Okay. So before I go back, and I will go back to the same example and write the solution in a more, the way we will be eventually writing them, but I need to define the following idea. How to represent the solution. Suppose we have consistent system, and that's crucial. If it's inconsistent with them. In a consistent system, what are the basic variables? The variables that correspond to the pivot column or the column with leading entries are called the basic variable. And here I am talking about the augmented matrix. So the variable that correspond to the pivot column in the augmented matrix are called the basic variable. Now, free variable. The variable that correspond to the column with no leading are called the free variable. Okay. So again, what I'm talking about, this is the augmented. This column has no free variable, sorry, it has no leading. X3 is free. Those two will be the basic one. That's always will be the scenario because that's where represent the ease in which we can represent the solution. Now, when we solve a system, how do we solve a system? How can I give you all the solution? When we solve a system, we express, and that's crucial, the basic variables in terms of free variables only using back substitution. So the way we are going to represent the solution of a system that has infinitely many solutions is we give the basic variables in terms of the free variables only using back substitution. Right? Can I move the paper? Please let me know if I need to stay. So now I'm going to go back to the previous example and talk again about how we are going to solve the system by showing you all the solution, not specific one. So I go back to the previous example. So go back to example number 3. And the echelon form was 1, 1, minus 1, 2. You should guys have it. 0, 1, minus 4, 0, 0, 0, 0, 0. So first, I am sure I don't have inconsistency issue. This is 0 equal to 0. I don't have inconsistency. So this system is consistent. Now what we have to do is to pick the basic and the free. And so this is my leading here. There is a leading key and there is no leading key. So that's how we will solve the system systematically. So the basic variable are x1, x2. Free variable are x3. So we first decide which are the free and which are the basic. Now use back substitution to express free basic in terms of free. Basic in terms of the free only. I underline this because it's crucial, of free variable only. Okay, so what I am talking about. We decided what are the basic, what are the free. Now I'm going to write the system that correspond to it. So the system is x1 plus x2 minus x3 equal to 2. x1, sorry, x2 minus 4x3 equal to 0. And this is 0 equal to 0. I don't need to write it. Now I need to express all the basic in terms of the free. Means this is the basic. I have to express it in terms of x3. And this is the basic. I have to express it in terms of x3. So let us write the solution. The way we write it is like this. x3 is free. Means x3 can take any value we want. What about x2? I go from here to here. I'm going to solve for x2 in terms of x3. But in this case, this is very easy. x2 is for x3. That's what I mean by back substitution. Now, the first equation, I need to use it to solve x1 in terms of x3. So let's see what this gives me. x1 is 2 minus x2 plus x3. Am I done? Am I done, you think? No, because I was very clear. Everything in terms of the free variable. x2 is not free. So now we use the back substitution. So this is 2 minus. Instead of x2, I'm going to substitute. x2 is for x3. So I will substitute for x3 for x2 plus x3. It means this is 2 minus 3x3. So now I'm going to rewrite the solution of the system. So now how do we rewrite the solution? So the general solution, we call it the general solution or the explicit solution. That's how the solution of the system is. And that's how I want you to write it. x3 is free. Means x3 can take any value we want. x2 is for x3. x1 is 2 minus x3. And that's how we represent the solution of the system. And now it's very clear, the solution. So let us say now I ask you, give two particular solutions. You know, these are the general. Suppose I tell you, give two particular solution, anything you want, specific one. What do I mean by that? So that's the general solution. If I tell you, give two particular solution, what do I mean by that? Anybody can, I don't know, make sense out of my question? Okay, no problem. It means that give x3 the value 1. Yeah, choose two values for x3. Exactly. It means choose a bunch of values for x3. So one solution would be, I can pick x3 to be 1. You can see how easy now to find solution. A lot of them. x2 is immediately 4. x1 is 2 minus 3, which is minus 1. So this will give me the following solution. Minus 1, 4, 1. Infinitely many. I can pick another one. I can pick x3 to be whatever you want. You want it 100? I don't care. x3 is 100. x2 will be 400. And x1 would be 2 minus 300. So minus 298. That's another story, and so on and so forth. Okay, so once we write it like this, we actually seeing all the solution. I can give x3 any value, and then I can find x1, x2, and x3. That's how we are going to solve the system starting today. Now, if for those who a little bit remember 261 or calculus 3, this will actually represent the equation of the line, which is the intersection of the three planes. So that's really what we're finding is the line that will intersect the three planes. And we will talk a little bit more about it in section 1.4 or something. But this is really the equation of the line. That's really what it is. Please ask questions as you move on. Very good. So we're solving a system, and every time I'm stopping Q at the echelon form. Now the question is, what if I go to the reduced echelon form? We are from the echelon to the reduced echelon, we are only performing row operation, which means that we don't change the solution of the system. So my second part is, what if we go to the reduced echelon form instead of stopping here and then we solve? How will this affect the picture? Okay. So question number 2 is, not question number 2, I'm still working with the same system. I'm not changing it. And my question is the following. What happens if we stop at the reduced echelon form? So I will take the system in example number 3. That you want that you see it. The same example, I'm not really changing it. And the echelon form we got was 1, 1 minus 1. This is the echelon form we got. Now I'm going to move a little bit further and go to the reduced echelon form and stop right there. And then write the system that corresponds to the reduced echelon form. So remember that, as I mentioned last time, the position of the leading are always the same, whether it's in the echelon or reduced echelon form. The position is always the same. So I'm going to go to the reduced echelon form. Which operation I need to do? You guys put it on bright space on chat. What operation do you want me to do to go to the reduced echelon form? Scaling. Why do you want me to scale, Haley? I mean, I have a 1, I have a 1. Those are my leading. Why do you want me to scale? If I reduce minus 4 to 1, what's the problem? To reduce minus 4 to 1, I have to divide this row by minus 4. If I divide this row by minus 4, this is going to be divided by 4. I will lose the 1, which is actually an extra. So there is no scaling because I have 1 here as leading and 1 here as leading. Shall I repeat myself or understood? Good. Okay. So what we are going to do, you remember how we go from echelon to reduced echelon form. We start from the bottom. So since there is no leading here, the bottom leading, the one to the right, and then we create 0 above. So I will use this one to create my 0 here. So what we need is, as you guys said, I multiply the second row by 2, add it to the first, and then this is going to be my new row 1. So the last row I will not touch, it's a bunch of zeros. This row, that's my leading here, -4, 0, and I'm gonna make this into a 0. So this would give me, multiply this by minus, that's a 0, so nothing changed here. Multiply this by -1 plus 1 is a 0. Remember, in the reduced echelon form, the leading has to be the only non-zero leading. Right here, minus, that's a 4, -1, that's a 3, -0, that's a 0 plus 2. Okay. So now am I in reduced echelon form? The leadings are 1. I only have 2 leadings. And every leading is the only non-zero leading in its column. So this is in reduced echelon form. So now I'm going to do exactly what we did before, but there is a little bit of benefit from going to the reduced echelon form. And I want you guys to be able to see it. So immediately, once we hit whether the echelon or reduced, we decide about our basic and free. So since the position of the leading never changes, whether I am in echelon or reduced, so the basic variable are going to be this one and that one. Those are the basic, x1, x2. And this is the free because there is no leading. Is x3. Okay, so those don't change. Now I will write the system that correspond to the reduced echelon form. So now what's the system that correspond to it? The first row, read x1, there is nothing here, plus 3, x3 equal to 2. So now I'm going to solve verbatim like I did before. But there is one benefit. I want you to tell me what it is. The second row read 0x1, so it read x2 minus 4x3 equal to 0, and the last one 0 equal to 0. I don't have to worry about it. And now again, solving means, for finding the general solution means you express all the basic in terms of the free. That's what solving is. All right, so now let us solve here. Okay, I start with x3 because I know it is a free variable. x3 is free. And now this one, I want to solve, I want x2 because I have 3 solutions, x1, x2, and x3. I want to express every one of them in terms of x3. This will give me x2 equal 4x3. Now x1, I will pick it up from the first equation. This will give me x1 equal 2 minus 3x3. Okay, do I need to do any more work or I am done? What do you think? I'm done because I expressed all my variable in terms of the free variable. So what do you think is the benefit from stopping at the reduced echelon form? So this is the reduced echelon form, and this is the echelon form. What do you think the benefit? I want you to look at the reduced echelon form one more time and compare what's the benefit of it. One last step. Which step, Haley? What is this? What is it that the reduced echelon form make it a little bit easier? Writing x1 in terms of x3. Exactly. In the reduced, when we stop at the echelon form, and you guys will have the freedom to do what you want. I will not force any approach on you. Okay. When we stop at the echelon form, the first equation will always have, not always, but it will have the x2 term, which is a basic variable. Since it will have the x2 term, because we did not require a 0 in here, then when you do back substitution, you have to substitute x2 back into x3. So it's a little bit more work. When you stop at the reduced echelon form, by making the coefficient of x2 in this equation to be a 0, and that was is going to save you that there is no x2 in here, so you can express immediately in terms of x3. So there is really not much back substitution in this case. So that's what make it a little bit easier if we stop at the reduced echelon form. There is not really a lot of back substitution. I will be able to express the basic immediately in terms of the free variable. That's the benefit of the reduced echelon form. What's not beneficial in the reduced echelon form? What is really going on? What's the problem with it? That you will need more steps to reach it. So every approach have its advantage. The reduced echelon form, because you have to go from the echelon to reduce, and of course this is a simple example, so you need to do more operation. So that's really the problem with it. But if you have the reduced echelon form, and as most of you should know, your calculator give you the reduced echelon form. So if you want to solve a system, your calculator will give you the reduced echelon form. And then solving will be easy because you can immediately express the basic in terms of the free. You don't have much back substitution to proceed. Any questions before we go on? All right. My last example, again, with system, I'm going to take 4 variables instead of 3 variables just to elaborate more the ideas. Okay. So example number 4. Find the general solution of the system below. Now, our system, we don't have to have the same number of equations unknown. So no more that. We can have more equations than unknown, and we can have less equations than unknown. So that will be the situation. So now I have a system. So that's a system of this 2 by 4 system. So that's a 2 by 4 system. 2 number of equations. And this is the number of unknowns. And the question is find all the solution of the system. I'm already finding one solution is not easy, but I need to find all of them. The process is verbatim the same. We are going to take the augmented matrix and then reduce. So let's get started. 0, because there is no coefficient here. 3 minus 6, 6, 9. And a 3 minus 7, 8, minus 5, and 9. And for this problem, we are going to go to the reduced echelon form, not the echelon form. First, we practice this, and it will be easier to solve at the end. All right. You guys will have to tell me which operation I need to do at every step. What will be the first operation you guys will do? Quickly. Put on interchange, exactly. I need a leading here. I don't have one. I need to interchange. So the first one I will do is I will interchange R1 and R2. So it's a 3 minus 7, 8 minus 5 and a 9, a 0, a 3 minus 6, 6, 9. Okay, so now I have a leading right there. All right, again, first we have to get to the echelon form. So am I in echelon form? So I have a leading. Yeah, I am in echelon form. So I can stop here, but as you can see, to do the back substitution is a little bit complicated. So I want you to take me to the reduced echelon form in this particular situation. So what would be your next step? If I want to go to the reduced echelon form, what do you think should be the next step? All of you. 1/3 R2. That's a very good idea. As you realize, the second row, we have all the terms are multiple of 3. So if I divide by 3, minus 3, divide by 3, first I will get the leading to be 1. But that's not really what I care, but I will simplify tremendously this expression. So the second operation, we're going to scale the second row. As I told you, I want to go to the reduced for this problem, not the echelon. I will have 0, 1, minus 2. So when you scale everything. And this is divided by 3, which is going to give me 3. Remember, what you're doing is you're dividing the equation by 3. That's really what corresponds to. And now it's a 3 minus 7, 8 minus 5, 9. And my leading, as you realize, I tremendously careful with that. All right, all of you now, what will be the second operation that you want me to do? I'm heading toward the reduced echelon form. What do you want me to do? All of you in your head, at least say it. Exactly. I'm going to multiply the second row. I have to make this into a 0. 7 R2 plus R1. This would be the new R1. So let's do that. I will not touch the last one. I cannot touch it anymore. It's done. The second row is done. Now the first row. 3, 7 minus 7, it's a 0. And minus 14 plus 8, that's a minus 6. If I do any mistake, you guys correct me. 7 times 2, that's a 14. 14 minus 5, that's a 9. And 7 times 3, that's a 21. 21 plus 9, which is a 30. Very good. So my leading and my leading. Would you guys like to do any other operation? Remember, at this stage, we can stop anywhere we want. But getting to this echelon form is just to make the back substitution easier. So exactly, we divide by 3 because we can. Because this is a multiple of 3, multiple of 3, multiple of 3. So dividing by 3 is really a good idea. Let us say, for the sake of argument, let us say I have a minus 5 here. You don't have to divide by 3. You can stop here if you want and start doing the process, because dividing by 3 is going to make this one like minus 5/3, and you don't want to be dealing with fraction at this stage. So let me go back to that. So I divide by 3, the first one. Zero, 1, minus 2, 2, 3. I know that I'm not touching this one, and the first one will give me a 1 across the board. 0, minus 2, 3, sorry, my apology. I don't know why I put this. Minus 2, 3, and 10. I am in the reduced echelon form, and now I can start solving. All right. First, I decide which would be my free variable and which are my basic variables. So what are the basic? Remember, I have 4, and no, when you're solving, I want to see x1, x2, x3, and x4. I have 4 of them. So what's the basic variables here? Again, I go back here, and which column has leading? The first and the second. It means x1, x2. Okay, now what are my free variables? So now the thing, we have 2 free variables. No leading, so the free variables are x3 and x4. Okay, now we choose them. Step number 2 is we have to write this, express the basic in terms of the free. To be able to do that, we have to do the following. Sorry. We have to write the system that corresponds to this equation. So let us write the system. So the system is x1 plus 0x2 minus 2x3. As you realize, I immediately plus 3x4 equal to 10. That's the first one. Now I'm going to read the second one. It's x2 minus 2x3 plus 2x4 equal to 3. This is not the solution. This is not the solution. This is the system whose solution is equivalent to the other system. Now, to write the solution means I want x1, x2, x3, x1, x2 in terms of free variable. Now we are ready to write the general solution. So here we go. So the general solution. Okay. I want x1, I want x2, I want x3, I want x4. That's how we write it. x4 is free. We write free. x3 is free. We write free. x2, I should be able to express it in terms of those. So now this x2 here gonna help me to solve. So what is x2? It's 3. I solve for it plus 2x3 plus 2x4. Now I have x2. Now finally I need x1. I'm going to use the first equation to pick up x1. So x1 is going to be 10 plus 2x3 minus 3x4. Now, because I went to the reduced echelon form, I was able to solve all of them in terms of the free variable. If I had gone to the echelon form, it's okay, there is no problem with it. But then when the first equation will have an x2 in it. So I need to do back substitution to be able to find x2. And okay, Thomas is correcting me. What did I do wrong? Minus 2x4. Thanks, Thomas. That should be minus 2x4. Correct. Plus 2x3. Okay. And this would be the general solution of the system. Now, if I tell you, give me 2 particular solution or 100 particular solution, it's easy. So now, once you give, so if I want a particular solution, so 2 of them, in this case, to get a particular solution, you choose a value of x3 and you choose a value for x4, not only x4 anymore. So now you have a freedom for 2 variables. You pick the value you want, and then you can find x1 and x2. So let me make myself clear. So find 2 particular solutions. Okay, so I'm going to keep this in front of me. So 2 particular solutions. Okay, so first one I can make my life easy. I can give x1 equal x3 equal to 0. And then I will have the following. This is 0, this is 0. x2 would be 3. Very easy. And x1 will be 10. Plug them back into the original equation. They should both of them, all 2 equations have to be satisfied. And another one, I can take x3 to be 0, x4 to be 1, because I'm too lazy to do more math than that. Okay, now, x3 is 0, x4 is 1. What is x2? It's 3 plus 0 minus 2, 3 minus 2, that's going to give me a 1. What is x1? It's 10 plus 0 minus 3, 7. That's another solution. So we can have as many as you want, but this time we have two free variables that we can assign to them any value we want. Okay? Any questions? Great. Right. So now I give you a bunch of system, which is basically to show you all the possible scenario. And as you realize, we had the following situation. Sometimes we have inconsistent system, and this occur when we have the augmented matrix have this form, the last one non-zero. And then we can, if the system is consistent, we have 2 scenarios. Either the solution is unique, one solution, or we have infinite. To have infinite solution, we have to have a free variable. It means the column that corresponds to one of the variables should not have a leading. To have unique solution, it means there are no free variable. It means the column that corresponds to every variable should have a leading. So I'm going to write this into a kind of example, and then we write the rule. So existence and uniqueness. I'm going to a bunch of matrices, and each of the matrix below is the echelon form of the augmented matrix of a system. It means there is a system somewhere, we reduce it, and we get to the matrix I'm going to show you. In each case, determine if the system is consistent. If the system is consistent, I want you to tell me if the solution is unique or infinite. Is the question clear? I have a system, I reduced it, I get something, I will show you what I got, and you have to tell me that if you reach this stage, what can you say? Is the solution infinite? Do we have consistency? In case we have consistency, is that the solution unique or infinite? So I start with the first example. So you have a system, you reduce it, you get to something like this. I did not put particular number. Remember, a black square means it's a non-zero. It means basically a leading. And star, it means any number. So suppose you read something like that. What can you say about the original system, whatever it is? So originally, I have a system of 3 equations and 3 unknown. Absolutely inconsistent in this scenario. And this is what then? Because this row reads 0 equal a non-zero number. Not 0. Absolutely inconsistent. Okay, now example number 2. Again, I want you to look at it. Tell me whether the system, the initial system, infinitely or free or whatever. First, the initial system will have how many equations? 1, 2, 3 equations. That's the original system. And we'd have 4 unknowns. 1, 2, 3, 4, because that's the augmented matrix. Okay, consistent. Absolutely, I don't have any scenario like that. Consistent. Another question is it unique or infinite? Okay, absolutely infinite, because in looking at this, x, it's consistent, done. X1 is basic, x2, 3 basic, x4 here, x2 is free, because there is no leading term in here. So it means we have infinitely many solutions. Okay. What is x4 in this problem? So you reduce your matrix, you get here. What is x4? Can anybody give me the value of x4? 0. No. No, 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 no. It's not free. Why it's not free? Let us remember. This is the column that corresponds to x1. Right. It has a leading. x2, there is no leading. This is the free. x3, the column that corresponds to x3 has a leading. That's a basic. The column that corresponds to x4 has a leading. That's a basic. Is that clear? Crucial to understand the picture. So the only free variable in this is actually x2. Now I asked the question, what is x4? I did not ask x3 because we don't know. Why is I know x4? Because the last row read a non-zero number, whatever it is, times x4 equal to 0, which will give me x4 equal to 0, just because this is non-zero. This is 1, 2, 3, something, okay? So, done. Any more questions? Please, these are important for you to be able to handle those questions. Now, the last matrix. Again, the question is consistent, first, the consistency, what I care about. Second, consistent, absolutely consistent. I don't have 0, 0, non-zero term. Consistent. Question number 2 is it? First, this is a system of how many equations and how many unknowns. Before I go on, how many equations we have here? So the initial system that I reduced it and I got here, how many equations does it have? No. Sorry, Rodrigo. 3. I have 3 rows. It means initially I have 3 equations. How many unknowns? 1, 2 unknowns. Okay. After I reduced it, I got here. So originally I have, now if equation with 2 unknown, that's basically a line. So initially what I have in mind when I wrote this example is something like that. I have 1 equation equal to 2. I'm making up things now. You don't have to write this. And then I have another equation, 2x1 plus x2 equal to 4, for example. And I have a third equation, x1, minus 5x2 equal to 6. That's really what I have in mind. So I took this system, I reduced it, and I got something like this. So basically, I have 3 lines, and I'm looking at the intersection of 3 lines. So this system, the original system, is a system of 3 equations with 2 unknown. It means basically I'm looking at the intersection of the 3 lines. That's the original system. And then when I reduced it, I reached that. Okay, so it's definitely 3 equations. And it is consistent absolutely. And now once I guarantee the consistency, I look for variable. This is basic, and definitely I have a unique solution. Okay, so that's when we have a uniqueness because there is no free variable and it's consistent. Does the number of lines correspond to the number of equation? Do you mean the number of rows, Haley? Yes, yes, the rows, the number of equation. The columns, except for the last one, are the number of unknown. So number of equation, you hide the last one, the number of unknowns. Okay, like in this scenario above it, 3 equations, that's the augmented term. These are the constant term of the equation. And you have 4 unknowns, 1, 2, 3, 4. And these are the constant term of the equation, the one to the right. Right here again, 3 equations and 3 unknowns. Okay. Another question concerning those. All right, so let me summarize this in the following theorem, which is, I think it should be understood at this stage. So, theorem. A linear system is consistent. I mean, there is a solution. If and only if the rightmost column of the echelon form of the augmented matrix, I'm talking about this row, this column, the rightmost column of the augmented matrix of the system has no leading entry. It means that is, the echelon form of the system has no row of this form. I mean, there is no leading in the augmented term. So a system is consistent if the echelon form has no leading in the constant in the augmented column. Make sense? Please ask as many questions as you want. Now, if a system is consistent, it means the rightmost column doesn't have a leading. Then we have either uniqueness or infinitely many solutions. The solution is unique, it means there are no free variables. If there are no free variables, and this will occur when every column of the echelon form, except the last one, of course, the rightmost, that's not what we care about, every column has a leading. So if every column of the coefficient part, every column of the coefficient part has a leading, like this scenario, then the solution is unique, granting consistency, Now, solution is infinite if we have a free variable. It means this will occur if the column that corresponds to at least one variable has no leading. So we have infinite solution if at least the column that corresponds to one variable has no leading. In case we have consistency. If we have inconsistency, we're done. So if the system is consistent, infinite, we require free variable. It means no leading in one of the column of the variable, consistent, unique. Every column should have a leading entry. Okay, any questions before we go on? So I will stop at this stage. Do you guys have any questions? Okay. Okay, thank you very much. The homework will be on Brightspace very soon, and the recorded lecture will be done around 12:30 because I have a class right after your class, so I don't have the time. Okay, bye-bye, guys.